Okay, so I'm kind of confused on this part. Like, I expected, I thought we would have to turn into like a 0.48 kilo in kilomega. So, like, how come we didn't need the kilo over here for these?
Okay, yes, that's a really good question. And here, let me clarify that for you. That had to do with week two. And let's go to week two PowerPoint.
Okay, week two.
I'm going to go to week two PowerPoint, and I will put it on the screen for us to share. And it had to do specifically with proper engineering notation. So let's go to here. Okay, let's start with this. All right, let me go and do a share screen with you. Reiterated. Okay, you can see my share screen now, yes?
Yes.
It's the PowerPoint. And this is week two. This is the most recent version, this version 4, it's in Canvas. And this is slide number 14. This is engineering metric notation. Engineering metric notation comes about from this slide. So this slide goes to show all of the different symbols for the different prefixes that reflect different powers of 10. And here are the English words, all right? So when we go to do calculations, the purpose for using scientific engineering notation is because we're dealing with very large numbers in electronics. We're also dealing with very small numbers in electronics. We want to find a uniform way of expressing those answers. And the uniform way of expressing those answers is shown in this slide. So without your calculator having been set in scientific or engineering mode, when you first do a 10 volts divided by 470 ohms, we get this yellow highlighted decimal number, 0.02127, and so on and so forth. And it's shown in the display in decimal format. Your calculator can be set in the scientific notation mode. And if you set it in the scientific notation mode, and you recalculate, what it is that you will see on the display is the second display. The second display goes to show 10 divided by 470, gives you 2.1276 and change. But look at the power of 10. The power of 10 is 10 negative 2. And scientific notation is given simply as one digit, followed by one decimal point, followed by the rest of the numerals, and then the power of 10, and then a unit, which is amps. So you have 2 followed by a decimal point, followed by the rest of the numerals, times 10 to the power of negative 2 amps. So that is the beginning of our final answer. On your calculator, remarkable calculator for under $10, you have this engineering key. By pressing engineering, this automatically puts the numbers in what we call proper engineering notation, meaning it'll change the power of 10 so that the power of 10 is some multiple of 3. It's either negative 3, negative 6, negative 9, negative 12, or it could be positive 3, positive 6, positive 9, positive 12. But all engineering prefixes end with a power that is some multiple of 3. So the display goes to show us 21.2769595 times 10 power negative 3, and we write down amps. Now, we're not going to write down on our answer sheet 10 negative 3. 10 negative 3, we look at our magic chart. Here's your magic chart. 10 negative 3, we see, is pronounced as milli. What symbol do we use? We use the lowercase m because it represents thousandth. So in this particular case, the final answer, properly rounded to 2 digits after the decimal point, will be 21.28 milliamps. Now, the next slide goes to define what is proper engineering notation and what are our rules of rounding. The rules of rounding are shown by 2 YouTubes, which I won't play for you, but basically, our convention for this program, for all of our classes, is to round hundredth decimal place, meaning 2 digits after the decimal point, which means you have to look at the third digit after the decimal point in order to determine whether you round up or you leave the number alone. So in the case of the example that I show you on this slide, if the answer calculates to be 34.356, that third digit is greater than 5. See, the rounding convention is 0 to 4, leave alone. 5 and up, round up, right? 0 to 4, leave alone. 5 and up, round up. And that third digit's a 6. It's above 5. So you have to round up the 0.35 to become 0.36. And that's why on the slide, the rounded answer is shown as 34.36. Now, the lower half of this slide goes to talk about proper engineering notation. And it cites 4 bullet points. And you have to note these very carefully. These should probably be written in your notebook if you didn't catch this the first time around. And written in your notebook, it says proper engineering notation is identified with only how many digits in front of my decimal point. What's my slide say? 1 to 3. I have to have 1 to 3 digits in front of the decimal point. Second bullet point says, proper engineering notation is never shown as a 0.xx decimal value, such as what I've typed in. And if you take a look at what I've typed in, I put in 0.0345, and then I threw in a kilo volts. That's not proper engineering notation because there's a decimal, okay? There's a kilo in there, but it's not proper engineering notation. The next bullet point says proper engineering notation is never shown with 4 or more digits in front of the decimal point, such as my example. I have 2,793.9323, and then I threw in a milli and then amps. Yeah, I got an engineering notation in there. I got milli in there, but I still have 4 digits in front of my decimal point. Our rules are 1 to 3, not less than 1, which is a decimal, not more than 3, which is 4 and up. You have a marvelous solution in your calculator. All you have to do is hit the engineering key. If there's some power of 10, if there is some power of 10, that is other than a multiple of 3. So if we do this particular example, and you go to calculate that, you'll end up with what you have here. Now, I sent you let me unshare this. Stop share. Okay. And I sent you as an example a solution set that you should follow. And so in that example, we had ohms. So could you put that back up on the screen so your classmates can see? Unmute your microphone, boss.
The quiz? Or which one?
What you flashed on the screen earlier, when you asked me the question, I'd like the rest of your classmates to see.
Share this.
Perfect. So as we're looking at this paper, you were asking me for the resistors. How come the first resistor is not a 0.48K?
Oh, is it because if you did that, it would become 0.480? There wouldn't be a number after the 8? Or is it because like there's
it would have been a decimal. It would have been a decimal value in front of your kilo, which is not proper engineering notation. Follow?
Okay, yeah.
Okay, okay. Where's that calculator? If I do it this way, and let's see if I can force it to do an error. Enter, engineering. Yeah, I can get it to go into smaller numbers, but not necessarily decimal bigger numbers. So anyway, and so the last number on that chart in that table was 2,270, and if you key 2,270, which is the sum of the first 3 resistors, into your calculator, and then you hit the engineering button, you will see it come out as, so 2,270 in the calculator. And if you hit the engineering button, enter and then engineering, it'll come out 2.27 10 power of 3, which is kilo. So that is the correct way in which these answers are supposed to be specified.
Okay.
Okay?
All right, good now. Thank you.
You're very welcome.
I have a question.
Please.
On the lab activity student guide, on the very last one, number 10, the question that it asks at the end, why it does not, why don't the calculated figures from the previous paragraph agree with the actual measurement? I'm stuck on that one.
Well, why don't you put that question up so everybody can see it?
I have it on I was just doing it on paper.
Okay, so where's the question from?
It's from the 4-page assignment, 3-page assignment, the review questions homework.
Oh. I have a quick question.
Yes, what's your quick question?
So for the parallel resistor calculations, I did them in my notebook. Can I take a picture of that and send that in?
For the parallel calculations, can you take a bit? Yes, certainly. Yeah, I've been taking them. We've been accepting pictures all along the way.
And did you want it in PDF form, or is it okay to leave it as a JPEG?
Well, how many pictures are you uploading?
Just one.
Okay, one is fine. As long as I don't get 6 pictures or 10 pictures. You know?
Okay.
Because I've had students say, can I send you pictures? Yeah, but the pictures were supposed to have always been pasted into a Word document, so I only opened one file, and as opposed to 10 files, 10 pictures from 25 students, and it just, that one assignment all of a sudden becomes 250 things that this man has to open. So no, one picture is fine. One picture says, speaks 1,000 words. All right, so let's see. We want to go to home and we want to go to week. It reads, for question number 10, what would happen if a wire had no resistance at all, were connected directly across the terminals of a 6-volt battery? How much current would result according to Ohm's law? That was the question that you were asking for, Gregory? Okay.
Yes.
And, yeah, Canvas is opening. It's just being slow. And suppose we short a 6-volt battery in the manner just described and measure 8 amps of current. Why don't the calculated figures from the previous paragraph agree with the actual measurement? Okay, let me tell you what's going on there. So let's go ahead and take a look at this one together and review questions, homework, and upload. It's trying to process 2 things at the same time. So when we talked about shorts, when you go to, we talked about short circuits and we talked about dead shorts. And so what we have here is a situation where we're dead short. That's the reason why there may be a difference is because there could be an internal resistance to the battery and it just doesn't drain immediately. Okay, so that's the fundamental reason why there may be some difference. Basically, what you do with any battery, if you take a 9-volt battery like this guy right here, and you put a bare wire across its terminals like this, and the tip of the metal, the tip of the pen is metal. If I go to do, it won't spark. There's not enough juice in here to cause a spark. But what'll happen is if I keep this in here for a while, the battery will get warm really, really quick. We found this out when we were kids, when we put the battery like this into our pockets, and our pockets had small coins in it. So a copper penny, a quarter or something touching across these terminals in your pocket, all of a sudden your pocket started heating up. You wondered why. And the reason is because the battery was being shorted. So, and so this would be a good example where the battery doesn't die right away. It doesn't explode because there's a reasonable amount of internal resistance in the battery, such that even though I short the terminals together, the conduction of current within the battery between the positive and negative plates, there is an internal resistance that is not allowing it to go to infinity in a moment and it die a moment later. It takes a while for one of these guys to die. And so while it's in the throes of dying, we can actually measure a current. It's pretty high, but we can measure a current. And so although we expect, for a moment, in theory, we expect maximum current for a brief moment until the thing dies, and then zero current after it is dead, in reality, depending upon the type of battery that it is, the internal resistance will keep the battery from dying right away. And it will drain depending upon the amount of internal resistance that we have. So that's the best way of answering that particular question for you. And did that help you out, Gregory? That's the reason why the numbers would not agree.
I had put dead short in infinity current for the previous
sure,
question.
And dead short and infinity is what we would have in an ideal voltage source. It would just dead short, it would go to infinity, it would burn out. Your car battery would spark and possibly explode because its internal resistance is nothing like the internal resistance of this 9-volt battery. So this won't spark. First of all, it doesn't have that much juice behind it, but the primary reason why it won't explode is because its internal resistance is pretty high. So you're totally on the right track with respect to an ideal battery.
Yeah.
This is not an ideal battery. This is a real world battery, and real world batteries have other considerations, and internal resistance is one of them. Okay? Good question. All right. So what else has this study group been tossing about back and forth?
I have a question.
I can help you all with.
How long will this go for?
How long will what go for?
The study group. Somebody asked in the Discord, what time will this go on until? Also, my class is starting soon, so.
Well, let's see. How long will it go for? I don't know. It might go. We might finish at 45 after. We might finish an hour at 7. It really depends on how many questions that there are that you all have asked. This is not planned as a supplemental lecture, but I've made this time available because you all said that it would be nice to put together the study group to begin with, and then it would be nicer that all of you can get together to review some of these concepts. And I thought, oh, well, that's commendable. And then when I saw the interchange of emails of things, how things fell apart yesterday, I felt sad that you all didn't get a chance to do what you had hoped to do. So I had approached one of your classmates and said, well, okay, how about if I open this up in Zoom, where in a format and a forum that we all are familiar with, that we have the assurance that yes, it can be recorded, yes, it's open to all questions, and yes, it's exclusive to the study group because you all asked for it. So I'm here to answer questions. I'm not here to lecture. Tomorrow is the lecture. So how long will it last? It could be over in the next 2 minutes, or it could be on for another half an hour.
Okay. Okay, I guess I'll check back later because my class is gonna start at 6:30. So thanks so much for putting all this together.
You're very welcome, my friend.
I have a question about tomorrow. The test, is that going to be, can we use our binders and textbooks and all that, or is it just the text?
Yeah, no, it's completely open book. It's completely open to almost anything. Just don't Discord each other. Yeah.
Well, what scenario was the notebook that you were telling us about? What scenario does that factor into for us?
Well, here, this might help you out. I gave you some examples during the last lecture of how your notebooks can come together. And let me share with you, and slide number 19, tips for success number 1. And it goes to show a journal or composition book. And it says your journal is your official notebook in any form that is convenient for you to write into. It can be a composition book. It can be a spiral bound notebook. It could be hard or soft bound journal, but it must be bound. No binder in this particular case counts for this journal, okay? Your binder is a separate thing, which I'll talk about separately. Now, this journal cannot have insertions, meaning you can't put Post-its in here. You can't put photocopied or printed materials in here. Everything must be written in your own hand. And you can use this in the future, when we get back to our on-ground courses. You can use this as an open book resource for any quiz, any test, any midterm, any final exam. And so I've shown you an example of the covers of different kinds of composition books. I like composition books because they're very compact. They fit into a backpack very easily. I don't care for the spiral, because the spiral, when you pull it in a backpack, they always get mushed up and fall to pieces. So I like something small and compact, like a composition book. And I like the quad rule, the graph paper kind. So I'm showing you in here an example of one page, and I happen to put in here some of the notes that came from the PowerPoint that I thought would be pertinent. What is likely to appear on a quiz or a test that I should remember? That's the guide as to what you should write down. You write down what you think you need to put down, because it's yours. You can do with it as you wish. Write down anything you wish, but you have to write it by hand. You can't, like I say, paste anything in here. So if you take a look at my page, I put down atomic theory. I've got something about the valence shell. I've got something about electron current flow, hole current, and stuff like that, different ways of freeing electrons. So that's page 1, page 2. Here's my page 3 and page 2 and 3. So I have law of electrostatics, and I'm showing the 2 different kinds of current flow. And so what I like about my journal is I can take my time after the lecture by looking at the PowerPoint and really putting down in my journal those points that I really, really need to have at my fingertips. If I'm taking a quiz, if I'm taking a test, what do I want to have in one place that I can get to, flip the pages, that has the information I need that will help me on a quiz or a test? So if I look at this page, does this page help me with respect to the law of electrostatics, that like charges repel and unlike charges attract? Does this show me the current paths? Does this show me polarities of each of the different current models? If I look at the page 3, does this define DC versus AC? Does it show me the different ways? This was a great question that Kirsten had asked. Different ways that DC voltage sources can be shown. Can it be 2 plates? Can it be 4 plates? Can it be 6 plates? It can be any one of those 3. They're all normal for DC voltage source. Ohm's law. Do you know the 3 different variations of formulas that can come out of Ohm's law? And then the electrical terms. Do you know your electrical terms between voltage, current, resistance, and power? Do you know the symbols? Do you know the units? Do you know the units for the symbols? Do you know the definitions of each of those? If you don't, it's nice to have this written down so that you can flip to the page and have it here as an example. If I go to the next slide goes to show a resistor color coding. So I have all the different, I have the mnemonic, bad boys race our young girls, but violet generally wins, good sir. And then all the colors and the corresponding numbers and the tolerances. And then I cite an example of a 4-band and a 5-band, what each of those bands represent. Then I have tolerance discussions down at the bottom. The next page, page 5, goes to show my engineering terms. Is that one place where I can reach with my hand and be able to get to what I want? So hopefully this will help give you some guidance as to what we mean by having your own journal in a composition book or spiral bound book, whatever, as I said, whatever works for you, that you put together the notes that are most helpful to you So here's an example. And then this isn't worth any points. This is worth gold to you during the quiz or test. What is worth points is your binder. Your binder is a repository of your work. It just goes to show me that you can organize your material in a logical, in a chronological fashion, and that everything is neat and orderly. So you don't have to buy a new binder. You can repurpose a binder. Here's an example of a binder. Throw in a few dividers, label the tabs of those dividers, and in each week, have we not had a list of deliverables? Would that not be an appropriate thing to have at the beginning of each section? And in all your handouts and assignments should be between each of those weeks. So here's this. Here's another one for another right here. That's week 3. So this is worth several hundred points by the end of the semester. And so I said Thursday we will be doing a binder check. Everybody's going to flip their binders for me at the end of the hour. So just demonstrate that, yes, you have something put together. And it doesn't have to be with fancy dividers. Some people can use Post-its or little stick-on tabs for week 1, week 2, week 3, but show me you've got some sense of organization, okay? Did that answer your question regarding the notebook?
Yes, it did. Thank you.
Okay, and you also now can go back to week 1, look at this PowerPoint, this updated PowerPoint, and see more closely at your leisure the examples of some of the things I put in my notebook. Okay.
So you're not grading the notebook?
I'm sorry, what about the notebook?
I remembered last week you said that the notebook was going to be graded.
Oh, that would be that you have one.
Oh, okay.
Yeah, no, I'm not going to be looking through the different pages of your notebooks, but I just need to see that, yes, you have one, that you're doing the little things that I'm asking students to do. What is worth a lot of points is, in fact, the binder. That is in your syllabus, and that's an absolute must. The notebook is pure gold, and it's for your own benefit. And if you choose not to do one, it doesn't cost you much points. But if you choose to do one, it's gold.
Would you mind just saying the things that you would be looking for? Because I remember last week you said you wanted us to have the engineering terms in it and stuff like that. I wasn't sure if that was required.
Well, whatever you, okay. Are you asking for suggestions of what should go into your journal?
Yes.
Yes. Anything and everything that you think can help you on a quiz or test. I have had students write out all the circuits that we've analyzed, and they've put every single circuit in the notebook. Some of the students have not. It really depends on what confidence you have with respect to those circuits. So for example, between circuit F and G, maybe I'll put circuit G in the book because we have at least 2 worksheets with respect to circuit G. One worksheet with respect to circuit G was a VIR table, VIRP table. That in and of itself is pretty beefy amount of analysis and calculation. And then the other aspect of circuit G that I would put in the notebook, the journal, would be the voltages at specific points. What is the voltage at point F? And why should the voltage at point F be what you think it is when the switch is open and when the switch is closed? Can we reconcile that? And if those fine points are something that may be a challenge to understand now, those may be good things to put in your notebook so they won't be a challenge when you refer to it later on. So for each stint, what you put in your journal, your notebooks, will be different because each of you have your own comfort level with respect to what you have a confidence for and what you think would be helpful to help you be confident in a certain concept.
Okay, that makes more sense. Thank you.
Okay. Okay. Yeah. There's no hard fast rule as to what you need to include, but what I've included in the journal that I've constructed as an example, for sure, resistor color codes, for sure, engineering notation, those two tables, for sure, my electrical terms. Okay. That the minimum of those three should be in there because we use them all the time. You got to know the difference. You got to know the unit for current. And you got to know the symbol for the unit for current. You got to know the unit for power. You got to know the symbol for the unit for power. You got to know your engineering prefixes. What's the difference between a milli and a micro? If that's not clear, you better have it in your notebook so that it is clear when you flip to that page. It's, oh yeah, 10 power negative 6. That's not a pico. That's not a tera. That should be a micro. And what symbol should that be? So those three, I think, are just absolute musts.
Okay.
Because we use them
even
all
if we feel like confident, they should still be in there.
No. I use them so much I don't even think about it anymore.
Yeah.
But I thought I'd include it in my sample notebook because many of us are just beginning this adventure into electronics.
Cool.
Yeah.
Thank you.
Good questions. Good questions.
I have another
All right.
question, if you don't mind.
Yes, please.
Will you be testing us on power factor?
Power factor, no. There will be no power factor questions on the test.
Okay.
Your test will very, very much follow the line of questions that you saw on the practice. So if you did not do well, some of you who did not do well on the practice quiz, do look very closely at my notes. If your score was anything less than a 25 and you walk into the test tomorrow and you did not read my notes, then you're not doing due diligence to yourself. If your score on the quiz was less than 25, you have to read my comments. You have to find out what it is that you had done that was an error that could have been done better. And this is the forum by which you can ask questions. This special study group that you all have put together. So if you've got a perfect 25 out of 25, that's great. If you didn't get a perfect 25 out of 25, ask me the questions. How can I do something better in which area? And I can clarify that for you.
Okay. Thank you.
You're welcome. And Mr. Navarro, you are back in. We can thank the faculty counselor. As students have counselors, teachers also have one counselor that takes care of all of the teachers, several hundred teachers. That counselor is very busy. And I sent her an email saying, okay, this is where we're at. Please fix this. And she jumped on it right away. So Carlos, you are back in Canvas and also back in ClassWeb.
Amazing. You'll see me loading things on there then immediately. Thank you so much. I had not noticed that, but I'll go on as soon as we're done here.
Perfect.
I have a quick question about the conductance.
Yes, what's your question?
To determine the G or the Siemens, I guess.
Yeah, conductance is the name of the concept. Siemens are the units, correct?
Right. So, for example, the first one, 5K ohms, was I putting on the calculator? Was it just typing in 5 exponent 3 equals reciprocal equals?
Precisely.
And the same for all of them then? Okay.
All of them.
'Cause when I added them all up, I came up with the final number of 54.95 K ohms. That's what the next question asked.
What do you mean when you add them all?
The engineering notation. So I added the 4 numbers or the 4 answers together. Is that what I
Were
was
you asked to add them together?
maybe I just interpreted that.
Yeah, I don't think you were asked to add them. That would be question number 9, question number 8 on your review questions. And it doesn't ask you to add them together. So let's take a look and see if so everybody on your calculators, we can do this while we're waiting for Zoom to Canvas to wake up. The first resistor is 5 kilo ohms. So what you do is you key in your 5 exponent 3, there's your 5 kilo. And what you need to do is you hit enter so that it is now formally entered into the calculator. Then you hit your reciprocal key and you hit enter one more time, or the equal key. And then you come to see something that is some power that is not engineering. You see a 10 to the negative 4th power. So when you see something that is not proper engineering notation, what do? You hit the ENG key. And when you hit the ENG key, what do you get for the very first one there, Gregory? What conductance do you write down?
I got 200 micro ohms.
This is conductance. Resistance is in ohms. Conductance is in different units.
Siemens.
Okay, so speak the whole thing.
200 microsiemens?
200 microsiemens is correct.
Okay.
Okay. Okay. And is that a lowercase s or is that a capital S?
Actually, I'm not sure.
It says so in the exercise.
Capital.
Capital S, correct. Okay. Because a lowercase s stands for seconds. And we use that in the sciences as well. How about 47 ohms? So clear the calculator, type 47, enter, and reciprocate that. What do you get for your second answer is some power to the negative 2. So you have to hit your engineering key. So Dana, if you had 47 ohms and you reciprocated that on your calculator, 47 reciprocal, what would be the conductance that you would write down on a piece of paper?
21.28 millisiemens?
Precisely. 21.28 millisiemens would be correct. Okay, because you have to round up, because that third digit is a 6. Beautiful. All right, and then the next one is 500 mega ohms. So Harpreet, 500 mega ohms is the resistance. You are asked to calculate what is the conductance if the resistance is 500 mega ohms. So you key in 500 mega into your calculator, and Harpreet, what do you have for your conductance? The third resistor shows up as 500 ohms, 500 mega ohms. So you key 500 mega into your calculator and you reciprocate that. What is your conductance? What do you calculate, Harpreet?
Yeah, so I got 2 to nano S.
2 the what?
Nano. So
2 nano.
S.
Well, S is what you'd write down, but how do we speak it?
Siemens.
There you go. So say the whole thing. Speak the entire answer.
2 nano Siemens.
2 nanosiemens would be correctly spoken. Perfect. Thank you so much.
Okay.
Great. And the very last one of the 4 shows 18.2, very unusual, micro ohms. It's tiny. It's really small. It's about as small as a fly fart. Pretty small. So 18.2 micro ohms. Question goes to Carlos Navarro. 18.2 micro, you key that into your calculator, 18.2 exponent negative 6, and then you hit enter, and you hit the reciprocal key, you hit enter, and engineering. What do you calculate as the conductance, my friend, Carlos?
55 55 kilo Siemens or kilo ohm, sorry. that correct?
Where's the 55 coming from, sir?
I'm sorry, 54.9 is what I have. Is that incorrect?
Well, read for me what you think it ought to be. It ain't 55.
So I did 18.2 exponent negative 6
Correct.
equals,
Enter.
right. I did equals, is that what you
And
mean,
then
right?
reciprocal.
And then
You
I
hit
did the
hit
reciprocal
equals
on the,
again.
and then I hit equal and I got that. Is that incorrect?
Yeah, the process is correct. The question is whether you're reading the numbers correctly.
1 second. Sorry, I got 54.9 on the calculator.
50, okay. So your 54 point, those three things are correct. And we want 2 digits after that decimal point. So 54 point what?
9.5.
95, followed by what engineering prefix?
Kilo.
Kilo is correct. And what units are for conductance?
Siemens.
Siemens is pronounced.
Okay.
Now say the whole thing, the entire answer. Could you speak the entire answer, Carlos?
Yes, 54.95 kilo Siemens.
Yeah, 54.95 kilo Siemens is correctly spoken. Perfect. Excellent. Very well done. All right. So you see, there's no 55 in here at all. We're not rounding to a whole number. So when you first started off saying 55, there's nothing that we're doing in this class ever in any of our classes where the answer would be read off as 55. We want the answers as shown in your calculator to the hundredths. So 54.95 kilo Siemens would be correct. Okay, cool. All right. And your classmate, because your classmate added them together, then the total conductance works out to be something very close to the 54.95 kilo Siemens, because it's such a big number in terms of conductance. But you're not asked to add them together, okay? All right, so Gregory, did that answer your question regarding that question number 8?
I think so, but just to clarify, to get the next part of that question was, to algebraically manipulate the equation to solve for R in terms of G. Were we just entering the G amount, the Siemens, and then onto the calculator, and then hitting the reciprocal key again equals
Your resistance.
and that equals, and it goes back to what the original value was.
That is correct. Yes,
Okay.
That's the purpose of that last part of that statement. Yes.
Cool. Yeah, that answered it. Thank you.
Mm-hmm. Good question. Good question. Who else has another question? These are good questions.
Professor?
Yes.
So on the homework, we're supposed to do those online assignments. And in the description, it says do numbers 1 through 8, but there are 12 of them. We weren't sure if we were supposed to do all 12.
Yes, you are supposed to do all 12. That
Okay.
was a typo. Sorry on my
Okay.
part. I'll have to fix that in Canvas. See, here's the thing. The course was never presented fully online. It's always been hybrid for all the years we've had the program. And so this summer, we did something special, something quite unique and different. And so in the conversion of the content from hybrid to fully online, some of the things didn't get updated quite the way it should have. So I'm glad you asked that question. Should those questions come up in the future, that's why we have a Canvas email, and that's why we also have really handy. This is the first summer session I've used Discord, and it's working out great. I really like the banter that I see between students in their questions to each other, and then also questions that come to me. It gives me a very fast method of being able to respond to students if I happen to be available at that moment. Somebody asked me a question at 3 o'clock in the morning. I'm probably not immediately available at 3 o'clock in the morning, but other times I might be in the supermarket and I see a ping, I go, oh, I can answer that. And then I'll respond, and you might get an answer in 30 seconds or less, sometimes longer. But it beats the regular turnaround time on Canvas, which is promised to be no more than 24 hours of a working day. So I really like Discord. Okay, what else have you all been discussing with each other that I can help with? Are there any issues with respect to the voltages on an open circuit in circuit G? Open switch. Is everybody okay with what those voltages should be based on your predictions and based on your measurements?
I'm not completely done with that assignment yet. And I know I asked you earlier, but I'm still confused on calculating the voltages.
Okay, in which side? The switched or unswitched side?
I think it's for the closed switch side.
Okay, the closed switch side. Let's go ahead and talk about the closed switch side. And what's easiest to do there is probably, let me switch this to, everybody can see this. Focus. Cool. All right. So we happen to have our circuit, and you are asked with the switch closed what the voltages are going to be at very specific points in the schematic. So the schematic goes to show this way. You have a voltage source, you have a resistor, a resistor, a resistor coming down here. This is where the LED would be replaced with a short, and this is where your switch is now in the closed position to here. This, I believe, was point A, B, C, D, E on this side, F on this side, G on this side, G on this side, G over here. All right. And you had very specific values for R1, R2, and R3. And I made a mention to you, Shisumaga, that this is easily, the quickest way to get through this is use voltage divider formula. So if I recall, don't we have a, let's see, let me go ahead and flip this guy over to here. We have a 2 kilo, a 1 kilo, and a 5.1 kilo ohm. Is that correct? Everybody with me? So far, so good? All right, let me do a full screen on this so we can, okay. So as we have this on full screen, it was a 2K, 1K, and a 5.1. Everybody okay with that so far? So why don't we very quickly do a voltage divider formula. So VDF is voltage divider formula, and I want the voltage for R1. So if I want VR1, that's equal to R1 over R total times my voltage source, which was 5 volts. So VS. Isn't that the formula for R1? I take the value of 2 over 8.1 times 5. Is that my fast math? Do I have to write kilo in the numerator? Do I have to write kilo in the denominator only because they're going to be canceled? Do I have to write omega in here? No, not when I'm doing math. Do I have to write volts here? Not when I'm doing the math. So here, it becomes nothing more than turn on the calculator. It's 2 divided by 8.1 times 5. Bam. You should be able to confirm we have right here 1.23 volts, yes? Okay, and then so now, Chisamaga, give me the calculation for VR2. What's the voltage on VR2? So you take 1 divided by 8.1 times 5. Do that now.
I got 617.28 millivolts.
Excellent. So 617.28 millivolts. Very good. All right. And now we're going to do the last one, which will be nothing more than 5.1 divided by 8.1 times 5. And so this question will go to Dana. 5.1 divided by 8.1 times 5. What's our last voltage?
I'm sorry, what? Can you repeat the question?
Well, we're calculating VR3 in this particular example.
Oh.
We're using voltage divider formula. So I
Okay.
said it would be 5.1 divided by 8.1 times 5. And your magic calculator spits out
3.15
3.15 volts. Perfect. Everybody okay with those numbers? Okay, then the next thing you have to remember, what determines polarity in any schematic that we work on? Who remembers what determines polarity for any schematic that we work on? Carlos, do you remember? Kirsten, do you remember?
The direction of the battery? For the voltage
The
source?
orientation of the plates of the battery, correct, yes. And in which direction does the battery push current? So the long plate is always going to be what polarity?
Positive.
Positive.
Okay, good. And the short plate will always be?
Negative.
Negative, good. The plates will determine the polarity of the source. Once we know the orientation of the plates of the source, that tells us how to mark polarities across these components. So the electrons will be pushed out of the negative plate down here, go this way, go this way, go this way, go this way, go up, and then go around the corner, go through this resistor, go through this resistor, go through this resistor, and end up at the positive. Is that the correct direction for electrons to flow in this circuit? So my electron flow is stated to be in what direction?
Counterclockwise.
Would be CCW, counterclockwise. Very good. Now, that being said, how do I mark the polarities across these resistors? Each resistor has its own positive negative polarity that is guided by this voltage source, that is guided by the direction of these currents. Who remembers what they are?
Would you mind repeating the question? Sorry.
Not at all. The question is, how do I determine the polarities that I mark across these resistors? How do I determine the polarities that I mark across these resistors? And
I would assume that going from the negative terminal of the voltage source to the first resistor, that would be negative, and then the other side would be positive, and then it would just go from there. Is that right?
That would be correct. So if I am looking at the right here, okay. So if I have the electrons flowing in this direction, and so I'm looking at the third resistor, 5.1K. I have this lead of the resistor, and I have this lead. I have the right lead, and I have the left lead. What polarity should the right lead be? What polarity should the left lead be, based on what I have drawn so far?
The right one should be negative, and the left one should be positive.
Does anybody concur with that? Have any questions regarding that?
I agree.
We have one agree. We have any other opinion on that? Okay, the agreement is correct. Remember that electron current flow will always leave the negative plate of the source, go through the circuit, and come back to the positive. Electron current flow flowing through devices, here's the device, here's the device, and here's the device, will always flow from the negative side to the positive side of that device. Electrons enter this side is negative, flows through it, the other side is positive. As electrons enter the second resistor, what polarity will be the right side of this resistor? Question goes to Chisamaga.
You're asking what the
What polarity should be on the right side of this middle resistor? Should it be negative or should it be positive?
Negative.
It should be negative. How many people agree this should be negative?
Negative.
I agree, negative.
Should be negative, and this side is positive, correct? That way it's consistent. It must flow through any device from the negative side to the positive. So as the current flows through the device from the right to the left, the right side must be negative, the left side must be positive. And the same must be true for this, yes? And do we have, in fact, a resistor that is physically attached to the positive side of the source? Therefore, the lead of that resistor shares the same polarity as that plate of the source. So this is positive, that will be positive. This resistor over here, the last one, R3, has a wire that attaches all the way to the negative plate of the source. So as this plate is negative and there's a wire all the way to this side of the resistor, that side of the resistor must also be negative. So you got to know the polarities across these guys, got to know the voltages across these guys. Now you can now determine what voltages we're playing with, okay? So let's go ahead and take a point. Let's go ahead and take a point. Let's call this, how about, let me find the, how about VB? And VB. So you see, V is the voltage. That's the physical quantity we're going to measure. And we want to measure it to point B. So since you're only given a single letter subscript here, that means you're going to put the red probe on point B. Where's the black probe going to go?
Ground.
Ground. And where is ground shown in this particular circuit? Ground in this particular circuit happens to be attached right here. Is this ground? Is this side also ground?
Yes.
Are these the same point? Is point G and point E physically connected to each other?
Yes.
Yes. Is there any resistor between them? No, it's only wires. This is a wire, jumper wire. Jumper wire switch is nothing more than a wire that's closed, and that's a wire. So if I have a point connected to another point and nothing between them, if I state this side is ground, that means this point is also ground. How about point D? Is anything between point D and E? Nothing but a piece of wire. So if nothing exists except for a piece of wire between D and E, and this is the same as ground, as this is ground, wouldn't ground also exist up here? Isn't this another point of ground? Are we good with this so far?
Yes.
Okay, okay. So now you are asked for VB. So this means voltage at point B, and here's the terminology, with respect to ground. This is a very common phrase. I spoke it several times. Let me remind you and reiterate this. This is how it's spoken. Okay, so this is voltage at point B with respect to ground. So that means I am going to take a jumper and I'm going to hook it to ground. And ground is at point D. G, F, E, all of these are the same point when this switch is closed. And I'm going to take another probe and I'm going to put this to point B, which is right here. Yeah. And I'm going to hook this up. Connect here and connect here. Well, that's the easy part. We never want to measure before we predict. So let's make a prediction first. Let me help you out. So what I'm going to do is somewhere in your collection, you have a red crayon or a red pen or something. Can I use this red pen and put it at point B, simulating the red probe of my multimeter? Could I also take somewhere here, yeah. Could I also take this black pen and put this at point D, which is ground, okay? So I now have a red probe here and I have a black probe here. Is this going to give me a measurement called VB, the voltage at point B with respect to ground? Is this the correct connection between my probes, yes or no? Chisumaga.
I can't see the board right now.
If you're not looking at the board, you're looking at my schematic. My schematic says my pen is at point B, which is between the two resistors, and my black probe is at ground. G is ground, F is ground, E is ground, D is ground. We've ascertained that entire side of the board is ground because there's a wire connecting them all together. My question again, if I want the voltage at point B and I speak it with respect to ground, is my red probe at B, where it should be, and is my black probe at ground, where it should be?
Yeah.
Okay, so your job, when you do this with a pen or pencils or crayons, or toothpicks, whatever you choose, is there voltage between these two probes? Is there a number here and is there a number here? Hallelujah, you betcha there is. So there happens to be 617.28 millivolts across this resistor, and there happens to be 3.15 volts across this resistor. Between these two, isn't that going to be the sum of these two numbers?
Yes.
Yes, it will be. And here's the key. What polarity will the meter read? I've mentioned this to you before also. How is the polarity of a voltage or current determined? The polarity of a voltage is determined by what the red probe sees, the very first polarities it sees as it's being drawn towards the black probe. And what polarity does the red probe see as we pull it towards the black probe? What do you see there?
Positive.
Positive. So you would do this. Your solution is very simply this. V at B is equal to a positive 0.61728 volts. Could I write this as a decimal? Isn't this in milli, this amount in decimal? I could write it that way. And isn't that going to be added to, because we're going to add it to the 3.15 volts. So when you go to add these two puppies together, what are we going to have? 3.76728 volts. Is that correct?
Yeah.
And isn't that going to be positive? Yeah. And since now we have a prediction, and the prediction came about looking at what was asked, voltage was asked. Where was it asked? At point B. No other point was specified. If no second point is specified, then it must always be with respect to ground. We put the red probe on B. We put the black probe on ground, which is down here, G. But we discovered that G is electrically the same as F because there's only a way between them, is electrically the same as E, is electrically the same as D. They happen to be the same point. This is ground at point D as well. Even though it's drawn here, it is ground. Then we only look between the two probes and we see we have those two values. Since we have those two values, you add them together. You start off with a positive 0.61728, go through it, and the very next thing we see is a positive 3.15. Add those together, you have a positive 3.76728. Now, that's our prediction. what we're going to do is we're going to check it with a measurement. And so with a measurement, I'm going to grab my power cable, hook it up here, turn on the power supply, bring this guy down where we can see this a little better, and bring the meter down where we can see this a little better. Set the meter. We predict 3, so I don't want this at 2 volts. I have to go to the next scale higher, which will be my 20 volt scale. And make sure this is set up in voltage, make sure those are good. So the moment I press my switch between these 2 points, I'm expecting something close to this. Now my power supply isn't a full 5 volts. My power supply is like 2.9 and change. So what I'm actually going to measure on this board won't be this number. It'll be a little less than this, but it will be positive. It will be 3, probably 3.4, 3.5 something. Okay, are we ready for my button push? Look at my meter. Wow, it's actually better. Yay. My power supply has good days and bad days. 3.71 volts. Is that pretty close to my 3.767? Yeah, pretty darn close. Considering in the real world of tolerances of resistors, it's allowed to be a little off, and plus my power supply is a little low.
I have a question.
Does this help? Let me finish with Chisumaga. So Chisumaga, are we good with this one point B with respect to ground and how we predict it?
Yeah, thank you.
You're very welcome. Who has a follow-up question? I know somebody has a follow-up.
I do have it.
What is your follow-up question?
So the circuit you just stated, that was with the switch closed, right?
Yes, because his questions were pertaining to a closed switch.
So if the same circuit with the closed switch, instead of D, if we measure at G, we should get the same value too, right? On a measurement?
Well, let's clarify your question so everybody understands what you're asking. You're asking for a V, followed by what letters?
B, same letters.
Oh, V at EB, same letter. So what is your question? If I put my red probe here at A and I put my black probe at ground?
So if we put our
red probe at B and here at ground?
Yes. So I should get the same.
You would like me to verify what we're saying. All right, I can do that.
Yes, I'm kind of confused in that thing, but it should be the same voltage though, right?
We will verify that. It's okay. So we can unconfuse this very quickly. All right. So let me pull this guy up. Okay. So we have the voltage at, and I'm going to put this right on G. So right now it is on G, which is right here. So are we happy in my circuit build? I have the red probe on B and I have the black probe on G.
Yes.
And I go to push this in, and what do I have? 3.71.
Okay.
And while I'm holding this, check this out. I'm going to hold this down. I have my 3.71. I'm going to move this to a different point G. I'm going to point G there. Is this still 3.71? I'm going to move this to a different point G right there, because this is where one side of the LED would have been. That's still 3.71. I'm going to move this black probe to the point F, still 3.71. And I'm going to move this black probe, let me hook it up better, to a different point F, which is right over here. Do I still get 3.71? So have I proven whether the black probe is at this point, this point, this point, this point, this point, or this point? All of these points here are electrically the same point. All of these points are ground. And it doesn't matter where my black probe is, as long as it's somewhere in that path, it's still ground. And if I look at my schematic, I will go to E. So now E is clear the heck.
So I got a question right there. So because we don't have a no load or resistor on that side, that's the reason we're getting the same value, right? Because
correct.
The ground.
One wire. Correct. There's no load, there's no resistor on this side. That's why this is all one continuous point, all the way to point E. I'm now at point E, which is the same as D. press the switch, I get my 3.71 right there. Okay. Are we good with voltage at point B with respect to ground and that all of these points are ground? I'd like to do something more interesting.
Yes. Can we try one more or
Yeah,
something?
I would like to try one more. And how about we say we want the voltage from, how about VC to A?
That's perfect.
Okay, C to A. All right. So let's go ahead, turn off the meter, because again, you don't ever want the battery to drain unnecessarily. So in this sample, you have VCA. So you're given more than a single point. You're given 2 points. Whenever you're given 2 points, then you have a very specific placement of the probes. So you will place the black probe. You will place the black probe. I know what I can use. I just need a black probe. Need something black. Okay, here we go. All right. So we're going to put the red probe on the first. We're going to put the black probe on the second point. Are we good with that?
Yes.
So the red probe is going to go to point C. So I'm going to take the red probe and I'm going to place it physically at point C. Is it physically at point C right now on my schematic? I'm going to take my black probe, and black probe goes to point A. So here's my black probe at point A. So now do I have a black probe at point A? Ta-da! So the question is, between these 2 points, is there voltage, yes or no?
Yes.
What do you see?
So if we add the voltage drop at a B and A, that's the closer we should see, close to that.
You want to speak that a little differently. Between point C and point A, there happens to be 2 resistors, correct?
Yes.
And each of those resistors exhibits a voltage drop, correct?
Yes.
So between C and A, we could, one method of finding the voltage between point C and A would be to add the voltages between these 2 probes, correct?
Yes.
So when we go to do so, one method, and I'll do this in blue. This is only one method because there's a couple of ways of doing this. One method is to start at the red probe. What does the red probe see as we pull it towards the black probe? Go ahead and call that out, Harpreet.
It should be a negative 6.1. So negative 617.28 millivolts.
Yeah, or I can write it as a decimal, same thing. And then we've gone through that. Then what do we encounter?
So negative 1.23.
We have a negative 1.23, so we're going to add that to a negative 1.23 volts. And when we go to add those 2 together, we will end up with a negative 1.84728 volts. Is that correct? Is
Yes.
that our prediction? Does that
Yes.
seem reasonable mathematically? And,
Yes, I get it. Yes.
and I said that was one method. There's an alternative. There's an alternate method. Does anybody see an alternate method? Abbas, Harpreet, Dana, Carlos, do you see an alternate method of calculating the voltage from C to A? If not, it's okay. Let me show you the alternate method. Watch this very carefully. I have the red probe at C, correct?
Yes.
Is my red probe presently, I'm trying to do this so that, okay, is my red probe presently at point C? Is my black probe presently at point A? So far, so good? They
Yes.
are placed according to the letters that were being asked of us. Well, one method was to add these voltages the short distance between C and A by going in this direction. We counted a negative 617.28 millivolts. Then we counted a negative 1.23. So that sums up to be a negative 1.84728 volts. How about we do this? How about we go the long way around? From C, the long way around, all the way to A. That is another way of reconciling your voltages. Check this out. This is absolutely wild. If I go the long way around, what's the very first polarity the red probe sees as I go to the right?
Positive.
Okay. So this will be a positive. How much voltage do I have here?
3.15 volt.
3.15 volts. I now have gone through it, and now the red probe continues until it runs into another voltage. What does it see now? Because it's still got to make its way to the black probe. What does it see now between here and the black probe? A what?
5 volts.
Oh, what do you see? What polarity?
Negative.
Did everybody see? We're going to add a negative 5.00 volts. And when you go to add this, this will become, everybody do this on your calculators, 3.15 and subtract 5. What do you get? Do this on your calculator. 3.15 minus 5 equals?
1.85.
No. Dana, what do you get?
Negative 1.85.
Negative 1.85 volts. If you didn't call out negative, you just call out 1.85, you were rushing through your calculator exercise, and you need to pay attention to the details. Your calculator clearly shows a negative. You have to call it out. You have to write it down. So was this an alternate method of calculating 1.85, which if we round this guy off would be a negative, in the blue number would be a 1.85. So how did we do that? We went the long way around, and we ended up with this. So that's how you know that your voltages around a loop are correct, is if you go the short distance around and you go the long distance around, you end up with the same number. We're good. So we're expecting a negative 1.85. Now we're going to measure this and see if we actually are going to measure negative 1.85. So we said C to A. So this has got to go to point A. Move all this up. This has got to go to point A. So this is a point A right here. That's where my black probe will go. And my red probe will go to point C. And I will go ahead and put the red probe at point C right there. So the red probe at point C. The black probe at point A right there. So do the connections on the board reflect our objective, voltage from C to A? Red probe on C, black probe on A. And when I bring in my multimeter, there's my multimeter, turn the little beastie on. Leave it on the 20-volt scale for just a moment. Press the switch. Does it show me a negative 1.82? Does it show me clearly it's negative? That's 1.80 and change, yes?
Yes.
Now, since this is less than 2 volts, can I get one more digit of accuracy if I change from the 20-volt maximum scale to the 2-volt maximum scale? I will do so now. And see if I get that digit. Yep. I have 1829 millivolts, which is 1.828 volts. Pretty good. Any questions about measuring voltages between 2 points, especially with this exercise, especially with 2 different ways of determining that value of voltage? Is this helpful to you?
Yeah. Do you think I could do the same thing with an open switch too?
Yeah,
I have
no,
an open switch right now. And what do we have? We have 0 volts. And I'm going to go up to 20 just to make sure we're on the appropriate scale. And why is this going to be the voltage at 0? Because with an open circuit, let me draw this really fast. So we have A, we have B, we have C, we have D, come down E. Here's point G, and the LED, this side was point G, and then have our switch. This is point F. Here's our switch, but it's closed. So this is also point F. And then here is ground. Oops, I meant to show that as open. I apologize. So I will go ahead and show this as an open switch. So now we have an open switch. So our polarity of the source remains unchanged. It is still positive on top, negative on the bottom. Is there any current flowing through these resistors at all with an open switch?
yes,
No. Oh,
Well, it's either a yes or a no.
wait.
Is there any current flowing when the switch is open?
No.
Open switch equals no continuity equals no current. Are we in agreement? There's no current because we have no continuity. So far, so good, yes? Okay. That being said, if there is no current, what is the calculated voltage across R1? What could be, turn my thing off, what would be my VR1? According to Ohm's law, according to our friend Ohm's law, there's V, I, and R, correct? If I want the V, don't I cover up the V with my finger and see what's left? I times R. Is that the method by which we can calculate voltage? Yes or no?
yes.
Okay. That being said, this is equal to I times R. What is my I in this case? 0 amps. What is my R in this case? 2 kilo. Would you key that into your calculator right now, everybody? 0 times 2 kilo. What do you get?
2.5 milliamps.
I beg your pardon? 0 times 2,000 is going to give you something other than a 0? Isn't the formula for voltage I times R? Isn't I clearly 0 amps?
Okay.
No continuity, no current means 0 amps. What is 0 times 2,000, which is on my calculator? That's got to give you a 0. Is that correct? 0 volts. Any questions on that? How about the voltage across R2? This is also going to be 0 volts. What's my voltage across R3? 0 volts. So take a look for a moment. If we were to measure the same point we did earlier, which was voltage at point B, single letter means you're going to have the red probe at that letter and the black probe is going to go where? Ground. So where is ground in this case? Right here. So I'm going to put my black probe right here at ground. There at B. And my red probe is going to go to point B, which is going to be right here. Okay. So, do this a little better this way. All right. So is my red probe at point B and is my black probe at ground? Yes or no? Correct.
Yes.
What is your predicted measurement of voltage between these two probes? You again bring this red probe towards the black probe. What do we see when we bring the red probe towards the black probe? Is B physically connected to A? Yes. Is there a resistor in the way? Yes. Is the voltage dropped along the way? No. So it turns out in this particular case, point B is electrically the same as point A. Point B is, and here's another phrase that I gave you before, is electrically the same as point A. B and A are electrically the same. There's no drop between them. It's not open. They are connected, but there's no voltage between point A and point B. So the probe at point B is nothing more than as if it were right here at point A. What do you see between A and ground? 5 volts, yeah? This is what you would have on an open switch. On an open switch, no continuity. On an open switch, no current. If there is no current, then there's got to be 0 volts, 0 volts, and 0 volts across each of those. So I'm at point B, and I said that point B is physically connected to point A through a resistor, but there is no voltage dropped across this. So point B must be electrically the same as point A. So having my red probe here would be the same as having my red probe here. What do you see between these two probes? Positive 5 volts. Let's go ahead and measure this to prove it. I'm going to put this guy at ground. There we are at ground. Switch is open. Move this to point B. So it's now physically at point B. There we go. And turn this voltage on to 20. And this is in place. And the switch is open. The circuit is powered, but the switch is open. And what does my multimeter say? Pretty close to my board, my power supply. I'm sorry, let me bring this down where you can see this a little better. So this is at point B, this is at ground. My circuit board is on, my switch is open. I am measuring the power source, and it is positive. Are we okay with the voltage at point B with respect to ground with an open switch? I'm looking for a confirmation.
Yes.
Affirmation. What do you think the voltage will be at point D? What do you think the voltage will be at point D? Way the heck over here at point D. So that means my black probe is going to be at ground, and I'm going to put my red probe at point D. So is my red probe presently at point D? My black probe is at ground. Move this guy out of the way for a sec so it's not distracting. Red probe here, black probe here. What do we see between the red probe and the black probe? Can I pull this towards the black probe and see what happens? What do we see between point D and C? Is there any voltage lost? 0. Are they physically connected? Yes. Could we say that point D is electrically the same as point C? Is point C physically hooked up to point B through a resistor? But do we lose any voltage across it? Not if there's no continuity, not if there's no current. That means point C is electrically the same as B. In fact, all of these points, because they are all connected with resistors, but there's no drop, D is electrically the same as A. So if D is the same as A, what do we expect between A and ground? 5-volt source, yes? Positive 5 volts in this case. So the same at B, same at C, same at D. That's our prediction based on following our calculations of Ohm's law. Is 0, 0, 0. They're physically connected. That positive will be sensed all the way over to here. Let me prove it to you with the measurements. Here we go. This guy will go to ground. And this guy will go to point D. So that's physically is at point D. This is physically at ground. We expected the same 5 volts. Guess what? That's my power supply. This is close to 5 volts as that power supply is going to get. With an open switch, because these points are all electrically the same because we lose no voltage across any of those parts.
So if we go to connection E, then it should be the same thing because it's before the.
Yeah, I can go all the way to F because this is all the same wire. I can go all the way to F and I will still get a positive 5 volts. So I can prove that to you by moving the jumper all the way to F, which is here. All the way to F on this side, on the open switch side, on this side, sorry. So this will be E. I have to be on the open side. This is E, this is not F. So that's at point E, and if I go to measure here, as long as I'm on the open side, I will get my voltage source. Anything D, E, all the way to this E, yes, will be 5 volts. Once I'm on the F side, what do you think? If I have my red probe at point F and my black probe at point G, red at F, black at G, what's between these two now? A bare piece of wire. What do we expect to measure between F and G on a bare piece of wire? Homework question number 8, week 2. What do we measure on a bare piece of wire of voltage?
0.
0. And if I go to put this red anywhere on this side of the switch, here's F, and I bring my red probe here, I get a 0. My power supply is clearly on, but I'm going to get a 0 because I am now on a straight piece of wire between F, through this wire, through this jumper where the LED used to be, through this jumper to the rail. This is nothing but a solid piece of wire. Any questions on that? Good questions.
So if we have to calculate the same thing, how will we show the work on it?
You don't have to show the work, you just put the number down.
Okay.
You use scratch paper to show your work. You don't have to show me the work. Just put down your prediction.
Okay.
Okay, cool. Good questions. All right. Any other questions?
I have to go right now, but thank you for the help.
You're very welcome. I knew that was a question that you had asked earlier, and I had asked you to connect with the study group, and I hope that you will continue to do so, Chisomaga, in the remaining weeks to come. We're entering week 4, so we have just another 5 weeks total to this course, so we're getting there. So definitely take advantage of connecting with the study group. They will be a good resource for you to bounce ideas off of, challenge questions, be challenged, challenge them, and collectively you will help each other further your depth of knowledge and understanding of electronics. So thank you for coming by, Chisamaga.
Thank you.
For the rest of you, you're welcome. You're welcome. For the rest of other questions that I can answer for you.
I have a quick question about like the recording. Is this going to be on YouTube also?
It can be.
Okay, yeah, I just want to look at like what type of questions were also asked when I was in class.
Okay, sure. Yeah. Well, when YouTube makes it available, excuse me, when Zoom makes it available to me, I will have to put the editor. My editor is, video editor is now reinstalled, so I have now full use of it. And once I edit the recording, then I can upload it to YouTube, which I'll be happy to do so.
Okay, thank you.
Okay, any other questions? Well, those were good questions, Harpreet. I really appreciate the thought that went into the questions, and I hope this session was helpful to you. So if there's no more questions, we'll sign off now, and I will look forward to seeing you all tomorrow.
See you tomorrow.
Yeah, sure. Thank you. Thanks.
Have a great evening. Take care now. Bye-bye.